Hello, this is the luckiest maths teacher in the world. Thank you so much for tuning into this video. So I need to start off with a confession. See, maths teachers have been lying to their student for years and years, perhaps even centuries. So I haven't been a teacher that long, but even so, I've been lying to my students. So how have we been lying to our students? Well, remember when you would have learned about prime numbers, maybe year 7 or whenever it was. So you would have been told something like 7 is a prime number because it has only two factors, 7 and 1. So we told you that a prime number was a number with exactly two factors, itself and 1. So why is this a lie? Well, they are prime numbers technically, but what we neglected to tell you was that the definition we gave is actually that of irreducible. So because in the ring of integers, 7 can only be written as 7 times 1. You can't write it as another integer times another integer other than 7 and 1. So that fact makes 7 not prime but irreducible. And similarly for all the other primes, we were told in the ring of integers 23 is a prime. That's because you can only write it as 23 times 1 or 1 times 23, which is the same thing. We told you a number like 24 was not prime because you could write it as, say, 8 times 3, or you could write it as 12 times 2. You could write it as the product of two numbers other than itself and 1. But that fact alone doesn't mean that 24 is not prime. It means that it's not irreducible, because the definition of an irreducible element is one that cannot be written as the product of two non-units. So in the ring of integers, so if we're talking about z, the two units are -1 and +1. So remember, a unit is an element of the ring that has a multiplicative inverse. So -1 and 1 are their own inverses. In the integers, 2 is not a unit because its multiplicative inverse, which is a half, is not a member of z, is not an integer. So the numbers that we've been calling prime, you can't write them as the product of two numbers where neither of the numbers is plus or minus 1. So 23, we can't write it as something times something unless one of those somethings is 1. 7, we called it prime because you can't write it as two numbers other than -1 and +1 multiplied together. If you want to write 7 as the product of two whole numbers, it will have to be including 1. So that's the definition of irreducible. So 24 was not irreducible because 8 is not a unit. It doesn't have a multiplicative inverse in the integers. Similarly with 3. The multiplicative inverse of 8, which is an eighth, the multiplicative inverse of 3, which is a third, are not integers. So that's why 24 is not irreducible. So the concept that we've been calling prime is actually irreducible, that you can't write it as the product of two non-units. And in integers, irreducible means that you can't write it as something times something where those two somethings are not plus or minus 1. So the definition of prime is harder to get your head around. So an element P of a ring is called prime if we have two other members of the rings, A and B, and we're told that P divides the product AB. So another way to say that is the product AB is divisible by P. What that means is in the ring, if you take AB and you divide P, you get another element of the ring. So if A and B are elements of the ring and P divides AB, implies that either P divides A or P divides B. So remember in maths, this or means one or the other or both. So what we're saying is if P divides AB implies that P divides A, P divides B, or both. So what does this actually mean? So let's actually look at it in terms of our integers again. So we know that 7 is irreducible, but it turns out 7 is also prime. So that part wasn't something we lied to you about. So what this means is you can pick any number that is divisible by p, and you can write it as the product of two numbers. One of them will always be divisible by p, in this case 7. So let's look at some numbers that are divisible by 7. So let's say 14, for example. We know that's divisible by 7 in the integers. That part hasn't changed, divisibility. So if I want to write 14 as the product of two numbers, a times b, in the integers, I don't have a lot of choices. I have 14 times 1, or I can write it as 7 times 2. So note here, I'm only looking at writing as a product of two positive integers because that's all I need to do. I mean, I could write it as negative 14 times negative 1, but all the stuff I'm saying would still be true if we included negative products. So note, in each of these products, 14, if it's 14 times 1, 14 is divisible by 7. So one of the numbers is divisible by 7. If I write 14 as 7 times 2, one of the numbers is divisible by 7. So if I take a number that's divisible by 7 and write it as something times something, something times something, one of those numbers or both of those numbers will be divisible by 7. So let's look at another example, a bigger number. Let's say 280. So let's see how I can write 280 as the product of two integers. Again, I'm only going to look at positive integers because for negative integers, everything I'm saying would still be true. So 280, how can I write it? I can write it as 280 times 1, but 280 is divisible by 7. I can write it as 140 times 2, but 140 is divisible by 7. So 280 is not divisible by 3, so I can write it as 70 times 4, but 70 is divisible by 7. I can write it as 56 times 5, but 56 is divisible by 7. I can write it as 40 times 7, or 35 times 8, or 10 times 28. I can write it as 14 times 20, and so on. Notice, in all of these, at least one of them is divisible by 7. Divisible by 7, divisible by 7. So I can't write 280 as the product of two other integers where neither is divisible by 7. If I write 280 as the product of two integers, at least one of them will always be divisible by 7. But note, that doesn't work if the number's not prime. So we know 14 is not prime. So look here, I can write 280 as 40 times 7, even though 7 is not divisible by 14. 7's a factor of 14, but it's not divisible by 14. And 40 is not divisible by 14. So this definition of prime doesn't work for 14, because 14 is not prime. I can write a number, a times b, that is divisible by 14, yet neither a nor b is divisible by 14. And that means that 14 is not a prime number. So this will work for any number that's not prime. So for example, we know 12 is not prime. So let's pick a number that is divisible by 12, like 24. So I can write 24 as 8 times 3, even though 8 is not divisible by 12 and 3 is not divisible by 12. So that means 12 is not prime by this definition. So I'm sure you're starting to see why your teachers have been lying to you, because this definition is much easier to work with than this definition. In fact, trying to prove or trying to determine whether or not a number is prime using this definition would be tedious and would take a long time. It's actually quite simple to prove a number is not prime using this definition, because you only need to find one counterexample, like I did there. You only need to find one example where this does not hold to prove the number's not prime, but it's much harder to prove that it is prime. So that's why your teachers will have gone with this definition of irreducible. But is an element that is irreducible always prime? And are the only elements that are prime irreducible? So it turns out that in something called a unique factorization domain, these two definitions are equivalent. What that means is, in a unique factorization domain, if an element is irreducible, then it is prime. If an element is prime, then it's irreducible. And it turns out that the integers are an example of a unique factorization domain. So that's why we can get away with using this definition, because anything that is irreducible is prime, anything that is not irreducible is not prime. That's why we can get away with it. So what actually is a unique factorization domain? Well, a unique factorization domain, or a UFD, is a type of integral domain. We need it to be an integral domain because of this. We can't have division if it's not an integral domain. So that's what we went through. One of the desirable properties of an integral domain, in fact, the reason that we study them, is because you can apply the cancellation law that we went through, meaning that you can divide. So a unique factorization domain is a type of integral domain. So all unique factorization domains are integral domains, but there are some integral domains that are not UFDs. So that should tell you straight away examples of things that are not unique factorization domains. So the integers modulo 6, for example, or the integers modulo 8, we saw that they are not integral domains, therefore they can't be unique factorization domains. So unique factorization domain is just a special type of integral domain in which each element can be written one and only one way, as the product of units. We're going to investigate that definition a little more in the exercises. But what I want you to get out of this video are the two definitions that are before you, irreducible and prime. I want you to understand them, and I want you to understand that those definitions are equivalent in a unique factorization domain. All right, I hope you've enjoyed this video. This has been the luckiest maths teacher in the world. Have a great day.